Yeah, so here to talk to you today about Chalk. We started this company about 3 years ago, and it served today about 25% of all card transactions or debit card transactions in the US. A bunch of other fintech applications, also some really cool things in e-commerce and healthcare. And I'm going to talk to you today about how you can build a feature platform with Chalk. I think a lot of what you might be thinking about when you think of a feature store is like a database that you write to. But what we want to do is connect you to where your data actually lives and be able to process it in real time. So what we're going to look at today is an example of a fraud application. So we're going to have transactions and users and credit reports and things like that, and try to figure out who the good users are and who the fraudsters are. So what's on the screen right now is a set of features for transactions. We've got simple scalars like IDs, amounts, memos, and that kind of thing. You'll notice it's all very Pythonic. Like you just put a little decorator on top of a class called features. And then you can define the features you want and put the comments in your Python, and we'll treat this as a kind of a DSL and get it syndicated to the web and any of your generated API clients. You can also have relationships to other bags of features. So instead of having kind of like flat tables, we want to model the richness in your data and say, well, I have transactions, they have users, users kind of have credit reports and many transactions that link back to them. They have trade lines on credit reports. So we want you to model all of the richness in that data and try to keep this as Pythonic as possible. So once you've kind of modeled this data, you can also write features in really terse syntax to say things like, show me the count of purchases where the category is food and drink, and it's from this time, and give me the count there. So we haven't done anything, though, to connect this to data. And so after we've written our features, we need to go hook it up to where the data lives. So we can do that. I'll show you kind of two ways. One way is by SQL, and another is by writing Python functions. So with SQL, we can just write a plain old SQL file. Like if I run this, we see some transactions coming back here. And we can say that it maps into a feature class, in this case, transaction, by way of the names of the columns that are getting returned. So here we've got returned column names like ID, amount, user ID, @ and memo, all of which line up with properties of the transaction. So what will happen is that at runtime, we're actually going to go talk to your Postgres database to go get this data out. We can do the kind of like reverse ETL thing too, but often managing all of that state becomes a real headache. And even at real scale, you can often just get the data from the source of truth. Now, pulling all of your transactions would, of course, be way too much and really slow down your application. So what we do at runtime is insert filters on here. So if you were asking for the transactions like for user ID 1, we would push down a filter or push down aggregations and projections into this query so you only get back the rows that make sense. Now, you can also write Python functions on top of this same DSL. So for example, as a really simple one, I could want to write a function that compares someone's name to their email. This is a great fraud signal. I just kind of want to know, like, does your name sound anything like your email? So I can pass in, I can say I require someone's name through the type signature of my Python function. So I need a variable called user.name or with the type user.name, and I need an email with the type user.email. And I'm going to compute the Jacquard similarity by saying, give me the length of the intersection of the characters in the name and email divided by the length of the union of those same characters. And that'll get me this name match score on my user class. So once we've written a couple of these features, we can go try something out. So we can say, hey, okay, that name match score feature, what's the value of that particular feature? And I can get that back. But I could also ask back for a little more data. So I could say, for example, well, you know what, show me all of the features of user. Or if we wanted to get a little crazier, I could say, give me actually a lot of stuff. I want to know, like, what does the user look like? What are the trade lines for the user? What are all of the transactions for the user? And what we're going to do to compute that is build a query plan. So there's no kind of concept of like a feature view or like a singular set of features I must be querying or something I must set up. Much like when you query your database and you say, here are the columns I want, here are the features I want, so too will we plan this query at the time that you need to go grab the data. So for this really complicated one here, this is what that query plan looks like. But if we jump back to one we ran to before that, this is quite simple. And so we'll start here. Basically, what we needed to do to compute someone's name match score was we passed in a user ID. So we needed to figure out what was that person's email. And then we needed to feed it through our Python function for computing that name match. So that's kind of what's going on with Chalk. All of this is running behind a C++ gRPC server, so we can go down to ultra low latencies if you want, including around the 5 millisecond range. But we can also process really complex queries and queries that need to process a lot of data. Now, the next thing I want to show you is that it's really easy to iterate on this and to come up with new features. So what we might want to do is compute a new feature, for example, for someone's fraud score. So what I'll do is I'll say, I want to make a new feature that says get fraud score. And I'm going to base it on some of the other features that we've written before. So what I'll do is I'll take in someone's, this name match score that we wrote up here. So let's take that one in. I'll take in whether or not someone was deny listed. So user.deny listed, and we can, see where this is used here. Someone is in a deny list if their email, appears in our deny list, which we load up from S3 in this case. And I could take in, I don't know, maybe how old their email is. So here's this email age days feature. The way we kind of compute this is that we work with a vendor called email age. And email age, given an email, can give us a big body of response that's going to be this email age response. And kind of downstream of that, we could say we know how to take someone's email age response and parse out some of the meaningful features from it. So this is kind of the idea behind Chalk. You're not explicitly linking any of these steps together. You're not saying like, please run this function, and then once you've done it, run this other function. You're saying these are some kind of providers of functions that could be used as part of a computation graph to go get an answer. So this is going to pull out that email age days feature, and we're going to use that in our new fraud score. So we'll say, we're going to decide that if you're deny listed, that means your fraud score is 1. Otherwise, sure, we'll try this. It's going to be the average of your name match score and your email age days. So I'll go put this feature on my user here. And what we'll do is go query for this feature value. So to do that, I'll hop over to the terminal here, and I'll deploy my change to a branch. So this is going to pick up my Git branch. In this case, my Git branch is called main. And all of that code will be running in my cloud. So I can go talk to production data stores. I can go pull out real data and see kind of what's coming back. Also, I can run all of this locally if I like. And I can run these queries against this branch to see what that fraud score would be. Now, we can see this new feature coming back, user.fraudscore of 259, which is going to be the average of my email age days and my name match score. Now, this is like maybe not the best feature, so we could go iterate on this a little bit. And we can do this even like just by watching our code. So I could say, for example, that I want to watch my local changes. And anytime we make a code change over here, we'll run a deployment and rerun that query so that we can see what the value would be. So just stretching this out a little tiny bit, let's iterate on this and say, well, if my name match score is greater than 0.5, that's pretty good. Otherwise, if my email age days is low, I'm going to say like that's pretty bad. And then the kind of default here is going to be 0. So I'll go save this change here. This will get picked up for the deployment. And then we'll see this new feature value come back. And now my fraud score has gone down to 0. So this makes it really powerful to be able to try things out like this. Like you can just kind of dream up an idea, code it, and query it either online, or you can run a big backfill. And what's really cool is that all of the same features can be backplayed because we're tracking when they're occurring. There's a concept in Chalk called a feature time. And the way this works is that if we return a feature time from any of our resolvers for any of our features, in this case for transactions, we're returning this @ column that we're tracking in our Postgres database for when a transaction happened. We can then go back in time and ask, what would the transaction have looked like at a given past point in time? So that lets us try out this fraud score in a backfill scenario and to say, what would happen if? These also execute extraordinarily fast. So even in these cases, for simple Python functions like this, we'll take this Python function and completely understand its AST and run this as an expression. So it's kind of an unfair advantage against Python, where we're kind of running this in just C++ as opposed to needing to go, grab the GIL and run these Python functions directly. So that's a little bit on what it looks like to iterate on some feature sets and come up with some new values. We can see what this also looks like in the web here. So every time we're running these queries, we're going to get back a link to the how these query plans looked. And under the hood, we're doing a lot of things. If you've ever looked at like Postgres Explain Analyze or Snowflake's query plan viewer to do things like merge joins and distinks and projections. There's also a lot of caching built in here. So I think sometimes when you think about feature store, you really want to know, can I like load up my feature store and can I unload from my feature store to query it? And one great example of that comes via expensive API vendors. So for example, let's say that I wanted to kind of clean up my transaction memos. And instead of using a provider for this, like a Spade, I actually want to use OpenAI or use Gemini to figure out, like, is this an ACH transaction? Is it a non-sufficient funds transaction? What's the category or the cleaned up memo? And so I can do that by also writing one of these Python functions. So I can say, given a transaction memo, I'm going to compute the transaction completion by asking my model, in this case, Gemini, what is the category? Is it NSF? What's the clean memo for this given transaction memo? Now, downstream of that, again, kind of taking this result type, I can say, well, given this completion, I know how to load that up as JSON and extract these fields here. But this completion is actually really expensive to compute. So I'm going to say that I want to that I'll tolerate a maximum staleness, we call it, of infinity. And this means that if I've ever computed this value for the transaction before, I don't want to recompute it. I just want to sample it from that online store. And so you can do the same thing too if you have like a bunch of data in Snowflake and you want to go put it in the online store on some cadence. You can kind of make those queries to pull back that data on a schedule, load it up, and have it available at runtime. So you really get the best of both worlds, where you can go compute stuff on the fly, really any arbitrary Python at all, including calling out to APIs like Gemini or to vendors like EmailAge if I wanted to go ask them for some data, or if I wanted to kind of even do it across these relationships. So if I wanted to say, given a username and a date of birth, I know how to go fetch the user's raw credit report and the user's ID. And then from the credit report, I know how to fetch someone's trade lines from the credit report, for example. But being able to model all of these relationships without having to confine yourself to like a fixed table allows you to kind of express things really naturally, like in the way that you would think about them as you're just trying to write like a little toy Python program, but with the kind of performance and scalability of a real production tool. I'm just briefly also want to touch on the fact that we've got all the normal like feature discovery and cataloging things here, so you can figure out like what features are being computed, what how they're being computed, on kind of what latencies, in which named queries. You can set up all kinds of alerts and monitors and things like that, and you can do all of that from the code. Finally, all this just runs in your cloud. Almost everyone we work with has very stringent compliance requirements, and so we deploy to all the 3 major clouds. I think that's about my time. I'd love to turn it over for any questions.